Okay, so we are doing our very last two AP equation types. So after this, you're going to have 3 days of just pure practice, which will be good. Give you some time. Starting with anhydrides. Anhydride means without water. So you know you have an anhydride equation when you are told water is added. These are really, really simple to identify. And water is going to be a reactant in these equations. So a couple of rules some you are already familiar with. The first is the Demo rule that says oxides are weird. The fancy name for oxides, we haven't really said it, have been acidic and basic anhydrides. So when you have a non-metal oxide, we knew that as a fake acid. Well now, and I really didn't mean to draw an arrow here, now when we add that to water, because it's an anhydride, we know that it makes a real acid. Okay? So the same is true for the metal oxides. The metal oxide, or the basic anhydride, which Demo called a fake base, if you add water to it, we call that now a real base. Okay, so you already know those two rules, and we're actually going to apply them in this anhydrous situation. The next rule, and this is going to be very similar to a push-up problem, if you have a metallic hydride, and by hydride, I mean a metal attached to H, like NaH, CaH2, or something like that, and you add water to it, we're going to get the exact same products as we did when we just add the metal to water in the push-up problems. What were those products that I wanted you guys to know? H2 and a base, which was always metallic hydroxide. So again, something you already know, but now just know that if it's a hydride or a metal, if it's a hydride or just the metal added to water, you'll get the same products. 3 looks crazy. Don't freak out about it. We're going to do a practice problem with it, so you'll see it's really not that bad. But if you have a phosphorus halide and you add water to it, you get a hydrohalic acid plus a phosphorus-containing acid. Don't freak out. It's not hard, and I'll show you later. Rule number 4, it's kind of new. A group 1 or a group 2 nitride added to water is going to give you ammonia plus a metal hydroxide. And last but not least, an amine. And you learned what an amine was. In complex ions, it was NH3, right? So an amine react with water. They react with water to produce a hydroxide ion and something called, don't freak out, an alkyl ammonium ion. Let me explain this really quick. We know an amine is NH3, right? But that was when it was attached to something. So you're not just going to have NH3, you're going to have some sort of carbon chain here with the NH3 attached to the end. So what's going on? This is a Lowry-Bronsted acid-base reaction. An H is going to pop onto there, making squiggle, 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 NH4+. That squiggle can vary, but all we're doing is moving and jumping, throwing the H onto the NH3, making NH4+. And that's what this alkyl ammonium ion is. This is the alkyl portion. That's the ammonia. And we're actually going to do a practice problem with that. Okay, let's do some practicing with these. These will be pretty easy for y'all, and I'm stepping over this. Okay, excess water H2O is added to solid calcium hydride, CaH2. So this is a hydride, and when you add the hydride, we're going to get exactly the same thing as if we were just adding the base. And what would that be? Good. And this can be either part or separated. It's one of the ones that are marginal. They can go either way. I'll take either that or the actual ions. So, or Ca plus 2 plus 2OH minus is acceptable. And then for balancing purposes, we need a 2 on the water and a 2 on the H2. Okay, so this is exactly the same as a push-up problem. So here is another problem just like it, and the only reason I chose this one is because this is definitely a strong base produced. So we have to split up the base. And that's already balanced. So that's an example of that hydride rule. Okay. So now let's look at dinitrogen pentoxide is added to water. Uh-oh, what do you see? Oxides are weird. So what type of oxide is this? Non-metal, so it's a fake acid. A fake acid plus water makes a real acid. The question is, we've got two options. We have two types of acids that contain H, N, and O. And what are the options we have? HNO3 and HNO2. So which one is it? Well, since these are not redox, we need to pick an acid where the oxidation state of that nitrogen is not going to be changing. So what is the oxidation state of nitrogen in our dinitrogen pentoxide? It's a 5. So we need to pick the acid that has a nitrogen with a 5. It's HNO3. So that being strong, we write that, and we need 2 N's, 2 N's. I see that gives me a -2, so right away I'm going to make +2. That so happens to balance me out. The beauty about this kind of problem, if you were to pick the wrong acid, it would not balance at all, and that would be your indicator. You could spend all day and it would not go. Okay, let's do the next one. Solid potassium oxide. Solid potassium oxide, K2O, is added to water. Oxides are weird. What is this one? The fake base. When we add it to water, we're going to make a real base. And what's the base we're going to make? Potassium hydroxide, which is strong. So we have to write it as split up. So we need 2 Ks. Therefore, I need 2 of those. Right away, I can tell. And that's it. Now, this one is the one that has a scary rule. But again, I don't want you all to freak. It's not hard. Phosphorus pentachloride, PCl5, is added to water. So the rule says we're going to make a hydrohalic acid. What hydrohalic acid do you think we're going to make? Hydrochloric acid. That's a strong acid. We're going to write it like that. Then it says a phosphorus-containing acid. Well, the acid, to be an acid, has to have an H in it. It has to have a P. Do you see any O's anywhere? No, we probably need to include that in the acid as well. So, again, just like last time, I've got 2 options for my acids. What are my 2 options? H3PO4 or H3PO3. What's the oxidation state of the phosphorus here? +5. So I need the acid that has a +5, and which one is it? It's H3PO4. Is that a weak or a strong acid? Weak. So we're going to leave it together. And that's it. And now we have to balance this. And so 5 Cl's, that means I have 5 negatives, so I want 5 positives. And that's balanced, I think. 3 Oh, I need four 4H2, so 8 H's, 5, 6, 7, 8 H's. There you go. So it's really not that hard. You just have to recognize that it's a chloride plus a water, a phosphorus chloride plus water. All right, don't let this one scare you. The only organic group I want you to know is the methyl group. It's not hard. You already know what methane is. What is methane? See what? CH4. Well, all a methyl group is a methane hanging off of like a chain of carbons. So here's your carbon chain. If it's hanging off, one of the H's has to leave in order for it to have room to attach something to it. So it's a CH3 group hanging off of something. You've already learned this if you were in pre-AP into organic. Okay, so just using some common sense now and nomenclature simply, methylamine. What do you think it is? Methylamine. Methylamine, that's it. CH3NH3. This is the squiggle right here. And we're going to bubble it into distilled water. So anytime you add an organic base to water, it's that Lori-Bronsted reaction I was telling you. H is going to leave and hop onto the ammonia, making methyl ammonium. That's where the alkyl ammonium ion word comes from. And what does it leave behind? The H minus. Again, that's super, super specific. Okay, hold on just 1 second. Okay, I know there looks like there's a lot of rules for our last type, but there's really not, because you actually know the majority of these. Main thing about addition reaction is you're only forming a single product. So the first two are kind of duh rules, basically that 2 or more elements can form a single product. Okay, but also 2 or more compounds can form a single product, and we'll see that when we get to our fake acid and fake base situation, which again, you already know. These next rules you already know because we did them backwards. You did them as decomposition. What did a metallic carbonate decompose to? CO2 and metal oxide. That's exactly what this is, but it's reversed, because it's an addition instead of a decomposition. I don't recall us doing necessarily a metallic sulfite. Metallic, but it's pretty straightforward. What is it gonna? SO2 plus a metal oxide as well. Same thing. And the last two, you're going to get sick of hearing it over and over and over again. What does a metal oxide plus water make? Base. And then a non-metal oxide plus water makes an acid. So our first example, magnesium oxide. Yikes. Magnesium oxide is added to carbon dioxide. What do you think we do? Uh-oh, they're oxides. They're weird. So what are we adding? What's magnesium oxide? Yeah, it's MgO, but what is it? A fake base. Plus CO2, what's that? Which is a fake acid. When we add a fake acid and a fake base, what did we make? A salt with no water. So what's the salt we make? Yep, magnesium carbonate. That's it. We have another one just like it, solid calcium oxide, which is a fake base, is added to sulfur trioxide, and I don't know if up there that was balanced, which is a fake acid. We make a salt again, no water. And what is our salt? Calcium sulfate. So those are pretty easy. So those are the examples of the second rule, two compounds coming together to form one product. This is an example of our first rule, two elements coming together to form a product. This is Chem 1. Couldn't be any easier than a Chem 1 problem. What is it? Calcium nitride, so it's Ca3N2. Don't know why there was hesitation. All right, this is the one that's very specific, and unfortunately for now, until you take organic chemistry with me next year, kind of just have to memorize it. I'm not real happy with this problem. It's one of the things that we're removing from the AP in about 3 years. Doesn't do y'all any good. But when you're in organic, I'll actually show the mechanism of this. But this particular reaction is an addition reaction. When you see boron trifluoride and ammonia, it's that specific. Or phosphorus trifluoride and ammonia, you do the following. Just write it down and then I'll show you why it works that way. Boron trifluoride plus ammonia. Okay, hang on to your hats. This is really hard. Yeah. Not anticlimactic. This is called, the reason this happens, and I'll explain it with Lewis dot structures, this is called a Lewis acid-base reaction. So instead of a proton being transferred like they are in the Lori Bronsted ones, the ones you're used to with rice tables and everything, this one's a little bit different. It's an electron pair that's transferred. And I'll show you. So ammonia looks like this. And you don't have to draw this out. I'm just showing you so it might be easier for you to memorize. And it has a lone pair right there. To remember this, remember boron the moron. Boron the moron's electron deficient, so it normally is just going to make 3 bonds. Phosphorus has the capability of doing the same thing, but it means it's got a lot of room in its outer shell. So what happens here, these electrons will actually be transferred and shared between the boron and the nitrogen, making a bond. And that's what's going on there. So just shove it together. That's all you have to do. The end.